Yeah, reading the directions is really good, everybody. And like loudly said that while they were all taking the quiz, and it was still 25%. I did have one person answer, even after stressing that the Denver Broncos will lose to the Cowboys this Sunday at the beginning of the class. They wrote the Dodgers. Not sure why, but it's a baseball team. Yes, I'm not sure. I don't know. That could just be a cultural difference as well, though, which is why I mentioned the Dallas Cowboys at the start. But yes, that's fair. All right. So from today's bell ringer, we are just going to continue on, and we're going to hit the notes here. So if you don't have your notes out, you should get them out. Today, we are going to look at 3.4, and I think we're going to get through all of it today, but we'll see. For 3.4, we are looking at how do we actually go about, or how can we classify rigid motions. Now, the word recall isometry is the same thing as a rigid motion. It's a single word that sounds ugly or fancy. I don't know how you see it, but we're just trying to classify rigid motions. How many different rigid motions have we seen? Carson, can you give me one of them? So these are all rigid transformations. Okay, translation is our first rigid motion, and we've dealt with it. It's along a vector or Instagram brackets. Cool. Give me another one, Ashley. Reflections. Reflections happen over lines, right? Now, preferably it's over the x or the y axis, but it could be over any line that we possibly want. Turns out the line y equals x that we saw on just one homework problem, there is a big significance to that when we get back to algebra stuff. So we have translations, we have reflections. Vincent, can you tell me the third? Rotations. Now, same thing as before, we want it to be around which point? The origin, and that's really nice and handy if we have like the coordinate plane set up, but we don't have to go around the origin. We don't need to be on the coordinate plane. We just need to be able to measure the angle and do it, right? Whether it's out in space or on the coordinate plane. Now, if we're on the coordinate plane and it's not the origin, we just move everything to the origin and then do it and move it all back. Cool. So we know that there's only 3 of them, but right off the bat, we start looking at examples like we did today, and we've seen others. If I put 2 or more of these rigid motions together, gentlemen, what do they do? Like, what do we call it when I say translate and reflect? There's a one word for that. We use this symbol. So for example, a translate by something and a reflection by something. The order is wrong, but it looks like this. What does this symbol mean? Love it. We're going to look at how do we go through and classify these things when we're looking at composing these rigid motions, or isometries if you'd rather. Okay. Now, this part, it's not crazy. I don't think when I read this theorem, it seems obvious, and I hope it's the same for you. But we're going to jump right in with theorem 3.3. Pretty small theorem chapter. There's no name for this, but check this out. If 2 or more rigid motions are composed, and there's a lot of different ways this could happen, right? We have 3 different types of rigid motions, and if we choose 2 of them, there's several ways that we can do that, right? 3 choose 2. As we look at it, give me an example of 2 rigid motions that we could compose together. So check it out. I'm just going to use my hand, and it's not on the video, but we're all here. If I take my hand here and I translate it, and you said, what other one? A reflect. So I'm going to reflect here. Did I change shape or size? So when I composed those 2, if it didn't change the shape or size, those 2 rigid motions composed, they make a single rigid motion. Do you agree that? Like, I haven't changed shape or size no matter what. What if I now add a rotation? Have I changed shape or size? No. What if I, from that rotation, I now translate again and reflect again? Am I still the same shape, same size? Which means no matter what, if I have 2 or more rigid motions, reflections, translations, or rotations, and I compose them, is it still the same shape and size? Yeah. So then, if 2 or more rigid motions are composed, the final image is same size and shape. Now, I've worded this a little bit differently than your book does. Conceptually, it's the exact same, but I'm okay with this. Another way to say it, though, is that if we compose two or more rigid transforms, the overall transformation is rigid. Nothing changes shape or size, but we can change location, orientation, that sort of thing. But same shape, same size, I think says the same thing. Okay, now there is one very particular one that we saw in the bell ringer today that gets used all over the place. And legitimately, it does get used in some form of this with pretty much any CGI computer graphic stuff that you might ever see. So when we saw the bell ringer today, it was made of two things. What were they? To make those footsteps. A reflect and a translate. Did the order matter? Like, we all went with it and we reflected first, then we translated. But since it's still up on the board, if I were to translate it first and then reflect, do I get the same thing? So the order winds up being irrelevant. Now, it turns out that when we compose a translation and a reflection, we get a new specific type of transformation. And it gets its own name because it's so common. We are going to define that as what is known as a glide reflection. Now, realistically, I would typically just refer to this as a glide, but it truly is a glide reflection. And all this is, the order is irrelevant. Can we just, I'm going to try to write it mathy, and you guys let me know if we need the wordy version. When we have a glide, it is simply going to be a reflection over a line, we'll call it L, composed with a translation over some vector, x, y, such that, or with the vector xy is our vector in this case, parallel to line L. Okay, this is a super mathy version. Okay with the mathy version? Do we want the wordy version? We'll definitely talk about it. Let's see if we can make sense of it before we do the wordy version on the paper. When I say that the vector xy is parallel to L, can you give me that in a different statement? Like within this context. And I'm going to put that picture up on the board just so I have it. If I do this, I'm just going to do two real quick. So here's a foot. Awesome. And then here's my line. And then here's my other foot. We all have a similar picture to that, right? Okay. If I translated or reflected first, it doesn't matter. But if I translate, am I going in this direction? No. It is exactly, if this is line L in our picture, our translation has to be what with this line? The exact same direction. Like, that's the big part of this. Now, we could certainly try to do it like this. Like, we could do this translation and then a reflection, but each step along the way, we wouldn't get this straight path. We would start to see our feet start to spread out a little bit more. So it'd be somebody walking instead of a straight line here. It's dumb, and I can only do like 2 steps, but they'd walk here, then here, and then here, and then here, and then here, and like they start to take this goofy stagger walk. That is no longer a glide. They have to be parallel. Do you want me to write the wordier version of that? Okay, so I'm fine with that. The bell ringer today was a glide. Now, immediately from there, we get one more quick theorem, and then like we're almost done with the section, which is crazy how short this one is. Awesome, I hope, but pretty crazy. Okay, so one more quick theorem. And we'll say this one is theorem 3.4. Your book goes through the proofs of these. And I wish that our book did only 2 column. They write big paragraph proofs and stuff. This one, we are not going to prove together, but we are going to use it. So here's the deal. I'm going to make a claim. All rigid transforms and then I'm going to have a comma, and their compositions. So in like real true example terms, if you give me a reflection or a translation or a rotation, or you give me a reflection followed by a rotation followed by a translation, as long as I'm composing them all together, we're okay. Turns out that any of these rigid transforms or rigid motions, isometries, and their compositions can be represented by a single rigid transform. Now, we've already seen this a couple of times. And we've only seen like 2 really specific cases of this, but any rigid transform and composition thereof can be represented by a different one-step process of a single rigid transform. Now, just to remind you of where we've seen this, and you don't need to draw it again because we've already done it, but I'm going to do it in pink, and this is just for think. So check it out. If I have these 2 lines that are parallel to each other, and I want to reflect over both of them, and I'm going to make this a little bit easier to see. So here it is. I could reflect over both of them, and we did this. Alternatively, a reflection over 2 parallel lines just takes this figure and does what to it? This is an old theorem from this chapter still, but so if I have 2 reflections over these lines that are parallel, it ultimately just looks like a translation. We can see that a single translation does the same thing as 2 reflections together, which is exactly what our theorem says. What if these lines aren't parallel? And I reflect twice again, which is still a composition of different things. What if it's this? How does this figure move? And I can't just use copy paste here. It rotates about this point. Now, if this is 40 degrees, then if I wanted to find the new spot, I would just go a little bit further than that. I would eyeball out 80 degrees, and I guess I can't do it nicely here because it's going to overlap itself, but it's just a rotation. This whole point winds up here somewhere, and I got to think this one out. Right angle's over here. Something like this, and it's just a single, that's not a right angle. It's just a single rotation, and we saw this theorem already. If we reflect twice, and it's just re-emphasizing with this. Okay, what's a theorem? Much more general question. What's a theorem? Not give me an example of a theorem, but what exactly is a theorem? Turn and chat. I'm going to call on one random person in about 60 seconds. It won't really take 60 seconds. I just need to find my drink because I'm parched. It's right here. Look at that. That was easy. You probably don't remember it as vividly as I do, but theorems are better than diamonds is what I remember talking about in class. Because even though Kay Jewelers claims that diamonds are forever, they're not. It's been proven true. It will always be true. It has always been true, maybe. I don't know that one with fact. But this is a true statement. It has been proven to be true. There's no doubt about it. What do we call something that we don't have to prove is true? A postulate. Now, there's one more word, and I'm going to look up the spelling this time. I think we've seen it in here. I'm in the wrong chapter in my book. That's strange. Okay, one more word, and we immediately get one out of this, is when we're looking at a theorem, oftentimes a particular theorem, much like this one, it leads us to some more statements that we can make with these things. For this, we're going to put a little follow-up here. Here's our actual theorem. And if we get an additional theorem because of this, it doesn't typically get called its own new theorem. Instead, we refer to what is known as a corollary. It's like a follow-up saying, hey, this theorem is true, but here's a specific case or something additional that winds up as true because of this. So a corollary to 3.4. Some places, and this is just a weird thing in math, there's a bunch of different ways that we do this. A corollary could be presented as a new theorem, and it is a theorem. It's also proven true, but it's just as a result of some other theorem right off the bat. Okay, so our corollary to this that we've already seen, specifically, if I know that a translation can be represented by a reflection, right? And a rotation can be reflected by 2 reflections, just like this. Could a single reflection be represented by a single reflection? That sounds like a dumb question. Yeah, of course, that's what it is. It's a single reflection. So if I see that I can represent a rotation with the reflections, and I can do a translation with reflections, are all 3 rigid motions just some variation of reflections? So she doesn't sound confident here, but check this out. I'm going to write this out in words because the language is ugly. You don't have to write this. I just want to write the logic. Rotate equals reflect And it specifically, it reflects over lines like this. Okay, so can rotations be reflections? I'm going to make that more clear. Can rotations be the composition of two reflections? Yes. Okay. Can a translation be represented as the composition of two reflections? So reflect, and it just happens to be over, instead of a crossing line like this, it'd be over these lines. And this is that silly one that seems odd. Can a reflection be represented by a reflection? And that one even feels odd to write. But what are the three rigid motions that we've seen? Can they all be represented by reflection? So not only, which we could do it, and there's other differences here, like we could probably find others at work, but the corollary is just exactly that. All, I'm going to write isometries, which is my rigid motion. All isometries can be found by composing reflections. And it doesn't matter whether it's a rotation or a translation or a reflection itself. They can all be made by reflecting stuff. Now, do you agree that this says essentially the same thing as our theorem did? It says, hey, I can represent with this composition of rigid motions. And it turns out that the additional little step forward is that not only can it just be with a composition, but we can do it only with reflections. We can do everything only by reflecting, which if we think back to that computer programming point of view, it means that, holy cow, the number of rules that we really truly need just went way down. Because I don't need to teach my computer how to rotate, I just need to teach it how to reflect. Don't need to teach it how to translate, I just need to teach it how to reflect. And I can do this over and over and over. So from this, here is our first problem and realistically our problem today. So example, I'm going to use a little editing magic. I want us to find the glide. So specifically, when we say the glide, we are very explicitly referring to the translation by what vector and the reflection over which line. Do you guys want the bigger paper here, like this, to stick in? Or do you want the smaller paper here? My left or your left? I'm sorry, I could have probably just walked that over to you. My left or your left? Anybody want this one? All the points will fit on this one. Okay, so if you want to take a piece of that paper and pass it on. Vincent, did you just take a piece of graph paper to stick into your graph paper notebook? You can, I'm just giving you a hard time. Interesting. If you want the big one or the small one? You have graph paper. Andrew, big graph paper or small graph paper? Okay. If you'll toss that over to Andrew, Camille, when you're done, I'm cool with it. Okay. Before we do this, good throw. See, I say that, but I just did the exact same thing to Ashley. So yeah, like legitimately, it was a good throw. It's the paper's fault. All right. We can obviously do this problem together, and I have no doubt that I can get the answer, and that I could probably drag you guys through it and make you get the answer. But what's the fun in that? I want you to help me find the answer before I just lead it. So I should have asked before I did this, what do you think is a good way to start this problem? Draw this. Sketch this image for me. We'll meet back up in just a second because once we sketch it, we'll have a much easier opportunity. I want to, we're going to break this down. What's a glide made of? It's a reflection and a translation. Now, there's one important part that you have to put on there. The translation is parallel to the line that we're reflecting over, and that part's important. It has to be parallel because otherwise we're going to get a rotation that shows up somewhere. Now, what do you want to deal with first? The reflection or the translation? I think the reflection is easier personally, but it doesn't really matter which one we start with. If we start with reflection, how do I make this? This shape isn't quite right, and you can't do this with yours, but I can, which is pretty handy. I'm only going to take this red triangle here, as much of it as I can, and I'm going to ignore all the other stuff. You know what? I'll actually just erase the other stuff here. Cool. So I now have that same piece, and it should be the same size theoretically. It is. is there a very clear reflection here? Now, like I can tell that if I have this computer, I can see it. Can you guys see reflections on your page? Like obviously you can't move it around, and it's not a yes, I'm good at math, I can, and no, I'm bad at math, I can't. Everybody's mind processes these things differently, and I obviously have no clue how your mind views this. Can you guys envision this on your page? Anybody that can't? Not sure that I believe you, but okay. So there is a reflection here. What line would we reflect over to get to that other spot? Like this point. So if I go over -2, okay, if you can't see that, I'm going to keep this one up for a minute and it's going to be there. If I draw a line of reflection right here, does it look like that's what it's reflected over? And I can tell that because from -1 to -3, this is a distance of 2. And from -1 to 1 is also a distance of 2. I've kept those distances. That's a line that I'm reflecting over. And I wish that there were a way that I could say like, oh yeah, it's obviously this. It just takes being able to see it in your head and checking stuff, for now at least. Okay, so now that I've locked that part in, I'm just going to call that part A since we've done it together. So on part A, I'm just going to say let's identify, or step 1 rather. If you want to call it step A or step 1, that's the same thing. I'm going to call it 1 in hindsight. Let's find the reflection. Find reflection. Now, on mine, when I did it, because I did this problem as well, I started with translation, but it's okay. Either one is fine. What line did we just reflect over? And it took maybe seeing it here. Maybe you guys could do it on your own. If you don't have a fancy computer thing to draw this on, what low-tech device or supply do you have access to in here? Tracing paper does the same thing, right? I will hook you guys up with tracing paper if you need it or want it. Okay, we had the reflection. We reflected R, that's our reflection. And which line did we just reflect over that we said we think it's going to work? What is this line? So Ray claims x equals -1. Anybody else in here ever been, geez, they're having fun in there. Anybody ever been guilty of getting y equals lines and x equals lines goofed up? Like it's natural, it happens because they flip, right? And x equals line is vertical like the y-axis, which is a strange idea. The easy way to remedy this in your head. This point, what is it? -1, 4? I'm pointing to it. -1, 4. What's this point? -1, 2. This one? Nuh-uh. Oh, wait, -1, 0. What was the same on every single point? The -1, and that's the x value, right? So that's how I can keep it straight in my head. That's how I know that this is a reflection over the line x equals -1. Now, if you want to sketch it, you can. I wouldn't put a whole lot of focus into it, but I know that this new figure winds up here, I believe. That's where my new figure is. Once I have my new one, if you want to draw this middle step, it's cool with it. Once I've done that, can I translate, since this was a vertical line, can I translate this in a vertical direction and get it to land exactly where I need it to? Yeah. Now, how far down do I need to move it? So 3 down. How far in the x direction do I need to move it? None. So we'll just say find translation. And it's really just being able to notice that these things work. And I'll show you how I did it because I did it the opposite order. But here we go. When I find this translation, it's going to be a translation. You said don't move any in the x direction, which is going to tell me it's a vertical movement, which is parallel to that line. And how far downward from 1 down to -2? -3. So 3 down. And check it out. We see that if I took this green one and I moved it 3 down, and it's going to get ugly and muddled with the numbers and stuff, but I'm just going to do exactly what I said. Here's this. I'm going to move it 3 down. 1, 2, 3. It landed exactly where it should. Now, when I did this problem, I did it a little bit differently. I just saw the order different. I see the translation first. And what I notice on mine when I looked at it is these are on the same x value. So when I looked at it, I said, well, if I can get down here and then reflect, I'm going to get the same shape. And that's what I see in my head first. I made note of the fact that C was the same. And I said, oh, well, let's just move straight down. And then as soon as I moved vertically, I knew that my line of reflection had to be vertical. And I could still draw it here and see, oh, yeah, it's right here. It doesn't matter which one we view first, as long as we take a little bit of time to find it. Now, in the end, we're not quite done. We were asked to find the single glide, right? All we've found at this point is the two pieces of my glide. For our final answer, there's two options that we can go with. Based on the work that we've done, I know how I'm going to write it now. What happened first in our minds when we did this problem together? We reflected, and then second, we translated. So when I'm going to write this with a composition of two different things, this composed with this for triangle ABC, which one goes on the left of this composed symbol and which one goes on the right? So we reflected first, it'll be closest. So here's my reflection over the line x equals -1. And then after we reflected, we then translated it how? And I don't really need you to say it. It's 0, -3, right? We just wrote it. Here's our single glide that took us there. Cool. This lesson, there's not a whole lot of substance within it. Does it feel okay-ish? And maybe more than ish, I hope, but we'll find out. We have like 8 minutes. We're going to get a solid start on the homework. The homework is not super long. You're going to come close to finishing if you work diligently for the next 8 minutes. But let's go ahead and get to our classroom. So third hour, here we go. And I'll fill in all the other details here in just a moment. That's not us. 10:23. Your homework today, this evening, is going to be homework 3.4. And you're going to find this on page 136. I want you to do problems 11, 13, 17, 18, 21, and 25. Okay. Again, homework 3.4 up on the board for you. I'm just going to fill in these other details that I always do. Lesson 3.4. This is classify rigid motions. And here we are. Cool. Like legitimately, you'll be able to get 2 or 3 problems done at least in the next 5 minutes if you truly start.